Use implicit differentiation to find dy dx in terms of y and x. When you're using implicit differentiation, what you're going to want to do is, let me rewrite this out and give myself a little bit more space. Okay, step one with implicit differentiation is you take the derivative with respect to x of both sides. So you d dx both sides, like this. When you take the derivative with respect to x, nothing changes. So on the left, the derivative of 4x squared is just going to be 8x, no big deal. Now, when you take the derivative with respect to y, you take the derivative as normal. So you would drop down the 3, multiply it to 2, that's a 6, subtract 1 from 3 and get 2. But if you take the derivative with respect to x of y, multiply dy dx to it. So you have to attach dy dx. Some teachers or professors might call that y prime. I like to call it dy dx because that's what it's giving me here. Okay. Similarly, the derivative of 4y would be 4. But since it's a y, you have to attach dy dx. So step one is you take the derivative of everything, right? And you attach a dy dx if you take the derivative of a y term. Now, what I do next is I'm going to group all of the terms with dy dx to one side. Happy news, that step is already done. So the next step, which would be like, I guess, step 3, is factor out dy dx. So I still have 8x on the left, nothing changes. Factor out dy dx, and when I factor out dy dx, that leaves me with y squared plus 4. Now, our job is to solve for dy dx. So we need to divide everything by 6y squared plus 4, 6y squared plus 4, right? That cancels out. And so you have dy dx, and let me flip things around to make it look proper. Dy dx equals 8x over 6y plus 4. And really the only thing that you could do here is notice these are all even numbers, so you can divide all of those numbers by 2, and you would be left with 4x over 3y plus 2. But that's your guy. You are looking at an answer with x's and y's in it because that's how implicit differentiation works. Fun stuff. Find the slope of the tangent line to the graph x squared plus 2y equals 11 at 3, negative 1. Now, the slope of the tangent line is a fancy word for derivative. The equation that I'm given, y is not all by itself, so I have to use implicit differentiation. So let me write out x squared plus 2y squared equals 11. Okay, these are the steps to implicit differentiation. D dx both sides. That means you are taking the derivative with respect to x of both sides. Okay, so the derivative with respect to x of x squared is just 2x, nothing fancy. When you take the derivative with respect to x of a y term, you still take the derivative. So drop the 2 down to 2, multiply them together, that gives you 4. 2 minus 1 is 1, so the derivative of 2y squared is going to be 4y. However, since we're taking the derivative with respect to x of a y term, you have to attach dy dx to it. Okay? Every single time. The derivative with respect of a constant is 0, so nothing crazy. Now my next step is I have to get dy dx all by itself. So let's subtract 2x from both sides, like so. That gives me 4y dy dx equals negative 2x. In order to get dy dx all by itself, I'm going to divide everything by 4y. So divide everything by 4y. Cross that out. And dy dx is going to equal negative 2 over 4, which is negative 1 over 2, so negative a half, right? And then x over y. Now this is dy dx. This is the derivative, which gives you the slope of the tangent line. However, I haven't plugged in my value yet. So if you're an x and you're a y, me finding the slope of the tangent line at that point is going to be negative x, which is 3, over 2 times y, which is negative 1. And that cleans itself up to negative over a negative, which is a positive. 3 over 2 is 3 over 2. My slope is that guy right there. Okay? So by taking the derivative, we had to use implicit differentiation. We did that. We plugged in our point at the very end, and we got positive 3 over 2. Donezo. For each problem, use implicit differentiation to find dy dx in terms of x and y. All right, so let me spread this out a little bit. Let me give myself a little bit more space. Wow, this is not going to be pleasant at all. 4x squared y cubed plus 1 squared. All right, here we go. Buckle in. Implicit differentiation involves me taking the derivative with respect to x of both sides, like that. Left side, easy peasy, you get 2x. Right side, not at all. Right side is chain rule. And if you remember, chain rule has some type of outside stuff, in this case, squared. And then you have some type of inside stuff, in this case, 4x squared y cubed plus 1. In order to do chain rule, you take the derivative of the outside stuff, keep the inside stuff the way it is for now, and then take the derivative of the inside stuff. That's where it's going to be a killer. Okay? So, the derivative of the outside stuff has me bringing down 2 and turning that 2 into 1, no big deal. Keep the inside stuff the way it is. So 4x squared y cubed plus 1. Now we are going to multiply everything by the derivative of the inside stuff. So I'm going to create my own section over here to do the derivative of the inside stuff because it's not going to be pretty. All right, so this is going to be the derivative of the inside stuff. The inside stuff was 4x squared y cubed plus 1. Taking the ddx of that, taking the derivative with respect to x of that guy right there, has me looking at you and saying, ugh, that's product rule. U would be my u, u would be my v, so I need to do u prime v plus v prime u. All right? So, the derivative of u with respect to x is going to be the derivative of 4x squared. Easy, 8x, no big deal. Multiply everything by v as is. So that would be y cubed, no big deal. The derivative of v is going to be the derivative of y cubed with respect to x. That's going to be 3y squared, but since we're taking the derivative of a y, you attach dy dx to it. Multiply that to u as is, so 4x squared. Okay? And then what we haven't done yet is the derivative of 1, which is nothing. So let's clean this up. So we've got 8xy cubed. 3 times 4 is 12. X squared, y squared, dy dx. So that's the derivative of the inside. So we're going to multiply everything to the derivative of the inside, which was 8x y cubed plus 12 x squared y squared dy dx. I guess what we can do is, since I have this whole guy divided or multiplied to that whole guy, and my job is to get dy dx all by itself, let's completely eliminate the blue guy. So let's divide everything by 2, 4x squared y cubed plus 1, 2, 4x squared y cubed plus 1. Okay, all of that goes away, and fortunately the 2's go away. So on the left, we have x over 4x squared y cubed plus 1. That's going to equal just what's here in black, so 8xy to the third plus 12 x squared y squared dy dx. Let's subtract this guy from both sides. So I'm running out of space here, so I'm going to do this. I'm just going to subtract make it look like that. Okay. Sorry for the silence. There's just not much to say. um, and now, oh man, now I'm going to divide everything. Oh, this is a nightmare. Divide everything by u. Ugh. So maybe the best way to multiply that out and the best way to make that look instead of dividing it is by multiplying both sides by its reciprocal. I just think that'll look a little bit more pleasant. It's still going to be awful. It's still going to be so bad. But if I multiply both sides by 1 over 12x squared y squared, 1 over 12x squared y squared, I can maybe do some stuff, but I don't know. I don't want to do anything with this. I just want to leave it like that. So what an abomination of a problem. dy dx is going to equal 1 over, I don't need that parentheses, not yet. I'll scoot you over. 1 over 12x squared y squared times the quantity x over 4x squared y cubed plus 1. So you'd have to distribute there if you wanted to, minus 8xy cubed. So that is the answer. It's awful. It's terrible. I mean, look at the original problem. It's going to be awful. It's going to be terrible, but we did it, and that is a possible looking solution. You could go further. But I won't because I don't have space. And these are my videos. I do what I want. But yeah, that's implicit differentiation that involved both chain rule and product rule. Puke. Thanks for watching though. Like and subscribe. Use implicit differentiation to find dy dx in terms of x and y. So we've got 3x squared plus 3 equals ln of 5xy squared. All right, so let me rewrite it. 3x squared plus 3 equals, leave some space, ln of 5xy squared. All right. When we take the derivative with respect to x, the left side, easy peasy lemon squeezy. Okay? So the derivative of 3x squared, 6x. The derivative of 3, nothing. The right side is going to be chain rule and something else. So chain rule says you have outside stuff. Take the derivative of it. So the derivative of ln of blah is 1 over blah. Okay, keep the inside stuff as is, like so, but then multiply everything by the derivative of the inside stuff. That's going to require product rule. So let's go off to the side and find out what the derivative of the inside stuff is. We have the inside stuff is 5xy squared. I will call u and I will call u v. Okay, so the derivative would be u prime v plus v prime u. So I know what u is. U prime is the derivative with respect to x of 5x, which is 5. And v prime is going to be the derivative with respect to x of y squared, which is 2y dy dx. Now, when you take the derivative of a y with respect to x, you have to attach dy dx. So what now? Well, we have u prime v is going to be 5 times y squared plus v prime, which is 2y dy dx u, which is 5x. Okay, so we're going to multiply this guy to 5y squared plus 2y, and let's move this 5x over and make it dy dx. Let's just clean it up that way. And I probably could have multiplied 2 and 5 and made it 10, huh? Probably could have, probably should have, and I probably will in the next step. What I'm going to do first is I'm going to multiply both sides, though, by 5x xy squared to get rid of u. Multiply both sides to 5xy squared. So that'll give me 30x squared y squared equals, nothing changes with the purple except I'm going to clean these guys up. So that's going to be 5y squared plus 10xy dy dx. Let's subtract 5y squared from both sides. Subtract 5y squared from both sides. So 30x squared y squared minus 5y squared is going to equal 10xy dy dx. Last step, divide everything by 10xy, everything by 10xy, and some simplifying happens, right? And we'll write it over here. 30, 5, and 10 are all divisible by 5, so 6, negative invisible 1, and 2. They each have an x. No, they don't. But they each, so the x's, there's no x in common, so x squared, x. But they each have a y in common, so y squared becomes y squared becomes y, and y is now gone. And so that leaves us with dy dx equals 6x squared y minus y over 2x. Implicit differentiation, kind of painful, lots of fun. Like a tattoo or a nose piercing. Like and subscribe. Find dy dx at the point pi over 4 when sine x plus sine y equals tan x plus root 2 over 2. All right, so x's and y's floating around. This has got to be implicit differentiation. So what we're going to do is we're going to d dx both sides. We're going to d dx sine x, easy, sine y, equals d dx of tan x, easy. And I'm going to rewrite this as 1/2 x to the 1/2. All right? That's how I'm going to rewrite it. So square root of 2. Wait, no. That's just a number. What am I doing? That is much easier. Oh, praise the Lord. I don't know why I overthought that at all. All right, so plus root 2 over 2. I love it. Great. That makes life a lot easier. I'm glad I don't have to deal with that. That was my big grunt. My main grunt was from that. All right. Derivative with respect to x of sine x is cos x. No big deal. You know that. The derivative of sine y is cos y. But since we're taking the derivative of a y with respect to x, we have to attach dy dx to it. That's going to equal the derivative of tan x, which is secant squared x. Okay, no attachments because we're taking the derivative of an x with respect to x. And the derivative of a regular old number is nothing. That's why I was happy to find out that was a number. Now what we do is we get the dy dx all by itself on the left. So let's subtract cos x from both sides. Subtract cos x from both sides, like so. Cos y, that's a koi, it's a fish. Cos y dy dx is now equal to secant squared x minus cos x. Okay, divide everything by cos y. And let's not bother trying to simplify anything because I'm just going to end up plugging stuff in anyway. So let me write it over here. Dy dx is now equal to secant squared x minus cos x over cos y. Let's plug in our points. Move you over. All right. So dy dx with respect to that point is going to be secant squared pi minus cos pi over cos y, which is pi over 4. Now, secant squared is 1 over cos squared. So if I wanted to, if you don't have your secants memorized, here's a fun little trick. All right. This is the same as 1 over cos pi squared, right? And so we know what cos pi is. Give me a minute to complete writing things out. We know what cos pi is. Cos pi is -1. So this is going to end up being 1 over -1 squared, which is 1, minus -1 all over cos pi over 4, which is root 2 over 2. So that gives me 1 minus -1 is 2 over 2 root 2 over 2. Multiply the top and the bottom by 2 over root 2, like that. And you get 4 over root 2. Which if you wanted to, you could simplify. It would be 4 root 2 over 2, so it would be 2 root 2 when all is said and done. Right. But, we're going to leave it like that. Or I'm just going to write this out because I said it. Like and subscribe, please, I beg you. What is the equation for the tangent line to the curve x squared plus y squared, a circle, equals 25 at the point -3, 4? All right, well, first off, equation of the tangent line requires slope of the tangent line, which is the derivative. So let's do that first. Let's find the slope of the tangent line by taking the derivative. Now, the only way that you could take the derivative of this guy, or the easiest way that you could take the derivative of this guy, is by doing our good old friend implicit differentiation. So I'm going to d dx both sides. I'm going to take the derivative of both sides with respect to x, like that. Okay, so the derivative of x squared with respect to x is 2x, easy peasy. The derivative of y squared with respect to x is 2y, but don't forget to attach your dy dx. That's going to equal the derivative of a number, which is nothing. Now I have to get my slope all by itself. Dy dx means slope. So I'm going to subtract 2x from both sides, subtract 2x from both sides. That gives me 2y dy dx equals -2x. Divide both sides by 2y, divide both sides by 2y, and that gives you dy dx equals negative, 2 over 2 crosses out, negative x over y. Now, this is my derivative of the slope with respect to x and y. I can now say you were an x and you were a y. Let's plug those points in. So my slope is going to be negative 3 over positive 4. So 3 over 4. So what I have is a slope of 3 over 4. If I labeled you x sub 1, y sub 1, I can now think point slope thoughts. Y minus y sub 1 equals m times the quantity x minus x sub 1. Okay. Plug in 4, so y minus 4 equals 3/4 x minus x sub 1, which is -3. So minus -3 is going to be +3, so let's save a little bit of time. Okay, so in order to find the slope of the tangent line, we had to take the derivative using implicit differentiation. I took my point, plugged it in, got 3 over 4. And when I got 3 over 4, I used the same point and point slope form to come up with an equation. Now, if for some reason you needed to do this and turn it into slope-intercept form, then distribute. You're going to get fractions. Add 4 to both sides. You're going to still get fractions. That's an option, but I'm sticking with this because that's good enough for me. Find dy dx when e to the y equals x squared over y. All right, so this is implicit differentiation. I'm going to d dx e to the y d dx x squared over y. Now the left side is not crazy at all. You take the derivative of e to the y with respect to x is still e to the y, but you attach dy dx to it. Okay? On the right side, you have quotient rule. Quotient rule says that if you have a u over a v, you're going to have u prime v minus v prime u all over v squared. So u in this case is x squared. V is y. U prime is the derivative of x squared with respect to x, which is 2x, no attachments. The derivative of v is going to be v prime, and the derivative of v prime is the derivative of y, which is 1 with respect to x, so you attach dy dx. So really that 1 is not necessary, it's just dy dx. V squared is going to be y squared. Like that. So the right side is going to end up being u prime v, so 2x times v, so y, minus v prime, so dy dx, u, x squared, all over y squared. So let's do this. Let's multiply both sides by y squared. So we get y squared e to the y dy dx. Let's clean up the numerator a little bit. So we get 2xy minus x squared dy dx. I have to get both of my dy dx's on the same side. So I have to add x squared dy dx to both sides, add x squared dy dx to both sides. That crosses out and gives me y squared e to the y dy dx plus x squared dy dx equals 2xy. Let's factor out the dy dx from both of those terms. When I do that, I get dy dx times the quantity y squared e to the y plus x squared, and that still equals 2xy. Let's divide everything by y squared e to the y plus x squared. And I'm left with dy dx equals 2xy over y squared e to the y plus x squared. And that's all I have to do here. I mean, not that it's all I have to do. It's not an easy problem, not by any stretch of the imagination, but it's not like I have to plug in numbers or anything like that. We just get a really gross looking answer. And that's what you get. Fun.